Welcome to the races where the fastest gas wins. We've talked about this before, and I introduced the concept of the root-mean-square speed as a measurement of the average speed of gas particles, according to the kinetic theory of gases. And now we have an entire video dedicated just to this one topic. How nice. We see that in our box, we have lots of particles, and not all of these particles are moving at the same speed. Some of them are running around like they're on steroids, and others are just like chilling, like kind of slowly, just chilling around. But most of them are moving at a medium-ish sort of speed. In fact, if you graph the proportion of the particles as a relation to their speeds, you end up with a particular distribution. So what we're doing here, we're counting the number of, let's say, slow particles. You have like 1, 2, 3. So there's 3 of them over here. High-speed particles, you might have 1, 2, 3, 4, 5, 6. Higher speed. Most of them are around the middle, so we have something like that. And then if we graph the entire thing, it looks something like this. And this distribution is called the maxwell-boltzmann distribution, this over here. Now, if you took into account the speeds and the frequencies of all of these particles and come up with an average. So you're looking at the speed of one, and then the speed of another one, and the speed of another one, you add them all together and then divide that by the total number of particles. What we'll get is we'll get the root-mean-square speed. And on my graph, it could be somewhere, I guess maybe over here. And the reason why this is not exactly at the most frequent speed point, I guess the medium speed point, is because we have a slightly higher proportion of higher speed particles than the lower speed ones, and so that will drag the average up. Now, if we increase the temperature, that's increasing the average kinetic energy, right? That's temperature. So as you'd expect, you can predict that the root-mean-square speed would also increase. And the graph of that new distribution will look something like this, after an increase in temperature. So we have the same number of particles as before, except now a higher proportion of them have a pretty high speed relative to before. And of course, as we said, the root-mean-square speed should also increase. Maybe to somewhere around, I guess, here. These are all guesstimations, by the way. Okay, and now we've understood or established the root-mean-square speed, at least conceptually. We're going to bring in some math. Let's look at what we know so far. We found that using the formula for kinetic energy, the internal energy of a gas was, let's just a spin off of the 1/2 mv squared. But we also derived from the last video that internal energy is also equals to 3/2 nRT. So it doesn't take much to say that is equal to that, since internal energy is equal to internal energy, right? Now we're going to look at the formula for the root-mean-square speed of 1 mole of gas particles. And that just makes everything a lot easier. Now of course, if you said I had 3 moles or 5 moles of gas particles, the root-mean-square speed shouldn't change, right? So for 1 mole, we will have Avogadro's number, 6.02 times 10 to the power of 23 particles. And we'll also have 1 mole. N over here is the number of moles, remember. And mass is the mass of 1 particle. I know that gets a bit confusing sometimes. And capital N is the total number of particles. So that and that are not the same. Okay, so having 1 mole of particles multiplied by the mass of 1 particle is the mass of 1 mole of particles, right? And that is known as the molar mass, given the symbol mm, capital M, capital M. So that over there is the molar mass. Next we can cancel out the 2, multiply 2 on both sides, and divide both sides by the molar mass. And you have a square over here, and we don't like that, so we're going to take the square root of both sides. And that, my friends, is the equation for the root-mean-square speed. That's the root-mean-square speed over here is equal to the square root of 3RT over the molar mass. Remember, this is all in SI units, so molar mass has to be in kilograms. Now this is really consistent with what we saw earlier, right? The root mean square speed would increase with an increasing temperature. Also, we see that the heavier a particle is, the lower its average speed is going to be. That's just like saying that with the same amount of kinetic energy, a heavier object would move slower. Let's look at this relationship further with an example. Actually, with a race. Let's say we're comparing the root mean square speeds of two containers of gas, one with N2 and one with O2. What is the ratio of the two root mean square speeds? Now each of these containers have the same temperature, right? So looking at the animation, once again, we know that the heavier gas is going to move slower, so this O2 is heavier, so this is probably going to be O2, and then faster gas will be N2. And that's just by looking at a periodic table. You know the molar masses, so just check that out. Our equation from earlier, root mean square speed. So certainly we can, if you wanted to, solve for each root mean square speed for each molecule. So for N2 at first, we can get that and slot everything in there and then get a number, and then slot everything in for O2 and then get a number, and divide one by the other, and that will give us a ratio, right? But oh no, we don't know the temperature, so we're in trouble now. We can't solve this question, right? Well, not so fast. Let's try dividing one of these by the other anyways, okay? I hope you're good at arithmetics here. Oh, by the way, that is the molar mass for N2 and that's the molar mass for O2, in case you don't know that. Wow! So we've gotten rid of all the variables except for the molar masses. And now the ratio of the root mean square speeds of both of these is actually the square root of the ratio between the molar masses of them. Well, inversed, if you notice. The blue and the red have inversed. But let's now slot everything in. And remember, this time we're going to use SI units because, well, in this case it wouldn't really matter, but if you use this formula by itself, your molar mass has to be in kilograms. Be careful of that. And voila, that's our answer. So that's as far as we're going to go for gases, but we're not going to completely get rid of what we know yet. Now when we go into thermodynamics, our gas containers are not going to be stationary anymore. We're going to get moving. See you soon.